Hey, Gabriel, are you doing okay on the quiz? Did you already finish?
I'm still working on it.
Okay. All right. Cool. Hey, Calvin, how are you doing?
Pretty good. How are you?
Good. Quiz go okay?
Um, yeah, it was fine. Like I understood it, but just plugging it into my calculator was a little stressful because I messed up a couple times. But
Yeah, hopefully, as you can probably guess, there will be something like this on the final. So hopefully it felt like good practice. how's your you guys' projects doing? I know we all had meetings, but does anyone have any questions about the project or how to do something with it? All right, well, that's probably good. What about with anything else in the class?
I guess maybe you're just not, or maybe you're not giving them to us, or I just had a question about like designing. Um, like most classes have like a couple design questions usually, like in their curriculum, but I've never really seen that with this course. Is there a reason why there's not very many like design oriented questions?
Yeah, that's a good question, actually. Hmm. So I would say probably the first reason is that I think a lot of the earlier stuff does not lend itself to design, to a lot of design problems, like because we're the first, really 2/3 or so, you kind of focus on these electrostatic and magnetostatic problems, and a lot of those need to be simple enough that you can, obtain these analytical results. Whereas this last section, the transmission line, is probably the most conducive to design, but I suppose I haven't asked as many like very specific design questions of you. So I do think there's at least one question that's a little more design oriented in this homework, but that's a good point, actually. I will think about that for the future.
I mean, it just helps me like visualize a little more because you actually get into like how things work better. But
Yeah, I think too, the other sort of struggle with this is that like, how you kind of need to learn like the basic circuits before you can design like the more like stuff using electronics or something. I kind of feel like there's a little bit of this sense where with electromagnetics, like you kind of have to take this class before you take like microwave engineering courses or antenna design courses, which is where more of the design happens. But it's pretty hard to understand electromagnetics without understanding the or like understand electromagnetics without understanding like the vector calculus as well. And so that in some ways sort of like pushes this off into the like a third year type course. And this kind of goes into this other question of just like, is it really even like, worth it to do it this way? And in some ways it's kind of like, this is just how it's done. So like, I feel like I don't have a lot of leeway to change it, but on other ways, like I can change small parts of the course. So yeah, I do like that idea of making a note of that for the future. Do you happen to be signed up for that RF engineering course next semester?
I wanted to, but I'm already at 16 credits and I'd have to go get a credit extension in order to take it.
Yeah, hopefully I'll teach that more often, and I haven't taught it yet, but my goal for that is there's like a lot of these electromagnetic simulator software. So basically, we had those, we looked at the Maxwell's equations, and there's software that can simulate those equations. And actually, it's kind of interesting. So basically, kind of give you an idea. Like you can, the way it works, the way these simulator software works is you like, let's say you have some model that you're interested in, some antenna, and it could be any shape. So you're probably the most familiar with like a dipole antenna, maybe you've seen on top of a car. All right, so that's basically, let's imagine it. This is a car. You got your wheels and an antenna coming up here. So with these software, right, this antenna is connected via a transmission line. So there's your antenna, there's some transmission line, and then you have a generator somewhere in the rest of your car. But these solver tools, you could try to figure out like how does this antenna work? And you have to somehow convert this from the 3D model to something that's probably a bit more simple. So you would probably take this into your 3D solver. So I'll put it on here. And then you kind of would imagine that this whole thing is in a box. And this is the inside of this box. This is where we're going to solve all the equations. And the bottom of this box will be like metal. It'll be like a ground plane. The rest will be air. But somehow you have to figure out how to solve this. And so you have to break down this structure. So we would break this whole thing down into small bits. And the way you do that is each little section, you would break into a small cube. And then on each corner of this cube, you could solve. Right, so we could solve for the E field in the X and Y direction, and the H field in the Z direction here. And then on this bottom corner that we can't see, we could solve for HY. Oops. And EZ. And for each time step, right, if you had a source, if this was the source of right down here, like if this antenna was connected to the source, we would say that we could start the excitation of this whole system from this source. So we say at time 0, it goes from nothing to being excited. And then we could gradually expand out from this like central excitation point, what's happening at each different corner of this. All right, so then you could calculate all of the E and H field at each corner here. And then you could go on, right, and there'd be another block adjacent to this that does the same thing until at some point, right, you have your antenna is broken up into like these small blocks where you're solving for the fields at each point. And so the smaller you make those points, you can solve for all the fields. So that's how this is how computational electromagnetics worked. There's a bunch of different ways to do these computations. And there's a lot of programs that do it. And you can think to yourself why this might be the case, right? Do you remember we had the differential form and the integral form of the Maxwell equations? And so the different computational EM methods focus on solving either the differential form or the integral form. And there's a lot of numerical methods that go into this. But the RF engineering course, you don't necessarily need to know all the gory details of how these equations are being solved, but you can just build structures like a 3D CAD, excite them, and determine what their structure will do electromagnetically. And so that's kind of more like building those types of things and simulating them, measuring them, doing that type of design is more of like microwave engineering. Or RF engineering. Or antenna design engineering. Usually these are more like graduate level type courses, graduate or advanced undergraduate. And in these, often you would say like, okay, this is where like the design comes in, is in those types of situations, you might focus on how do you design an antenna of a certain length that does what you want, or how do you design an antenna that fits in a certain space, works at a certain frequency, or is made of certain materials. So kind of a bit of a divergence, but hopefully that gives some insight into why first you usually learn like these, do a lot of like the basic EM stuff where we look at the calculus, and that gives you an idea of maybe how the computational EM might work, and then how it works when you transition from like these analytical solutions that we can solve into these solutions that really don't have an actual analytical result. So, I mean, yeah. So I don't know. Does that make sense? Am I just rambling?
No, that makes sense. That does.
Yeah. Because even think about, okay, this seems like a pretty simple problem, right? Let's imagine a 1 point charge that's positive and 1 point charge that's negative, like this. And right, we would have fields that look like this. But even this is really hard to get an exact answer of what is the field look like at some point in space out here, right? Like this is not a super easy problem to solve analytically. And if you have a whole system of charges, right, more than 2 charges, it'll just make it even more complex, which means that it's really hard to do design problems. All right, well, I think probably everyone's here. I've been just talking about electromagnetics generally a little bit. I want to remind you a few things about next week. Okay, so no class on Tuesday. And then on Thursday, you'll have a review with Zayed. And I think Zayed is here. Do you want to say a word or two, Zayed?
Yeah, the professor, I'm here.
Hi, do you want to just introduce yourself and say hi?
Hello, I'm Zayed Mohammed. I am a PhD student in electrical engineering, and I am a TA of this course.
All right, thanks, Zayed. So bring any questions about the final exam practice problems. Okay, so bring any questions that you have, and Zayed will know the answers and should have some ideas of how to solve them if you're still wondering about it. Okay. You could also, actually too, I'll make the homework 11 due at 23:59 on next Thursday. So if you have any homework 11 questions, you could ask those also. A lot of them are similar to the final exam practice. Okay, and then quiz 11. So this is due anytime. All right. It technically closes on, I think, December 13th. So just do it before then. I wrote in Moodle that to have it due on Friday, Friday next week. So like a week from tomorrow, just so as a reminder, but I believe it closes at 7 a.m. on Monday of the finals week. The final is on Tuesday, December 14th at 7:30 a.m. So please schedule with the testing center. All right, in the final, I finished writing it. There are 8 questions. All right, so 4 of them are transmission line theory. 2 are basically non-computational simple problems about Maxwell's equations. So basically, do you understand the meaning of, we looked at the 4 Maxwell's equations at various times, and there's, a number of terms in there. Do you understand what the terms generally mean, what the meaning of the equation is? So there's 2 questions about this. These don't have really any computation. They can be answered pretty quickly. And then there are 2 questions from exam 1 plus exam 2 material. All right. And then total points wise, these ones are worth like 60%. These ones are worth 10%. And these ones are worth 30%. Okay. Any questions about this? Okay. All right. So all of the cookbooks will be in the front. So there's a whole bunch of them, but at the very front, there's going to be just pages and pages of all the equations that we did. So you'll have all of those available to you. I also, in the problems that needed more information, like another equation or maybe a more difficult integral, I did add those in. So there are a couple problems that I added a couple additional pieces of information to it. So you'll have those available. Trying to think what else. I think that's basically it. All right, any questions? Okay. At least one of these transmission line problems is also fairly, actually 2 of the problems are computational, but you might be able to see how to solve them fairly quickly. It'll just depend on whether you have your good thinking cap on, I think. So, so a couple of these are not meant to take too long. So I'm thinking this should be fairly yeah, fairly doable in those 2 hours. There's only one question that is going to take a decent amount of work to do. And that one is worth the most points. So when you go through it, look through the problems, the one that's worth the most points will take the most work. But even that one actually has some tricks that you could use. So, okay. If there aren't any questions, let's look at the homework. Okay, so the first problem says a lossless transmission line is terminated in a short circuit. How long in wavelengths should the line be for it to appear as an open circuit at the input terminals? All right, so first of all, what kind of equation, or how should we think about this problem? What have we learned that could help us here? All right, so if we see something like this, what does this mean? If it appears like an open circuit, what if something appears like an open circuit? What does that mean?
The meaning it has some type of load on the end.
Has some type of load, and what is the impedance of that load?
Infinity.
Yeah, right. It'll be infinity, right? If you just have this, right? If this is just free space or nothing in between, right? If you put your multimeter across here, right, you would get the resistance or the impedance, right, is equal to infinity. Okay, so we have a Z open circuit, and it appears like this at its input terminal. So if we have this, what is it saying that Z in is? So if you measure Zn, right, so we have our transmission line like this. And we've looked in here. What are we seeing at Zn? So we have a lossless transmission line, and it's terminated. Let's think about this part first then. Let's start from the beginning. So we have a lossless transmission line, which we just drew, and it's terminated in a short circuit. So what is the impedance of a short circuit?
0.
Yeah, so that one is 0. Okay. So we have the load is equal to 0, but we want to know what this length is so that it appears like an open circuit at the input terminals, right? And these are the input terminals, right? So we're looking into this and we want it to appear as an open circuit. So if we want it to appear as an open circuit at the input terminals, what would Zn be?
Would it not just be infinity as well?
Yeah, so we want this Z input to appear as if it's infinity. Okay, so we're saying the load is short circuited, but we want to know how long this is for it to appear at the input as if it's actually an open circuit. Now we have another relationship down there that we can use. Right, and this is what we were using last time. Okay, so what can this simplify down to? So we know that the load is 0. What does this simplify into? So on your paper, see if you can write a simplification of this Zn. All right, so if the load is 0, what am I gonna get here? ZL. Does that look, did any of you get this?
Yes.
Yeah.
All right. So now the question is, what length will give this appearance of infinity? So essentially, when is this side equal to 0? When is LH, or sorry, when is the LHS side equal to infinity? And that's probably going to be related to this, right? Because this is, we have a lossless transmission line. We don't, this is not going to be an infinite value. This is some finite value. So when is When is this equal to infinity? What should this be equal to if you want tangent beta L to be equal to infinity? Let's think about. All right, how can we write, what is tangent? Is this, how do we write this? Do we write it like this? Yes, no?
Yeah.
Okay, so when, what value? What value of theta
90,
would lead this to be infinite?
90,
Yeah, if it was this,
yes,
right? Because this would be 1/0. Okay. So the question is, when is beta L equal to pi halves? And what can we write? Maybe, what did we write? What were we writing beta as previously?
pi over lambda,
Yeah. 2 pi over lambda?
yes,
Yeah. Okay, so the question asks, how long in wavelengths should the line appear? For how long in wavelengths should the line be for it to appear as an open circuit? So what value in wavelengths should this be so that this equals pi halves? What is L? As L as a function.
lambda over 4,
Yeah. Okay, so what does this mean?
means that L should be a quarter of the wavelength.
Yeah, and it means that it means that we can have a situation where certain line, even if we have a load that's a short circuit, every half a wavelength worth of line, it's going to appear like an open circuit, right? So if this is z equals 0, right, we have tangent. Right, so if this is L is equal to lambda half, right? At this point, we would see the impedance, right, as being equal to infinite impedance at this point. And then if we go another half a wavelength, right, we're going to see again that the input impedance looks like it's infinite. So even if you have short-circuited loads, they can appear as infinite at certain wavelengths of the line, and vice versa. If you have a open circuited load, it can appear as a short circuited load for certain wavelengths. Okay. So that's one of the kind of crazy things about transmission line theory, is that you can, if you're clever, you can often design things to take advantage of this, right? Where you can take advantage of the fact that your load appears open circuited or short circuited, even if it's not actually this. So you can do special designs to make this happen. And one of the classic ways of doing this, and this actually there's a bit of a design problem here, Calvin. So is something called the quarter wave transformer. And so this is a clever way of designing your transmission line in order to reduce reflections back towards your load. So if we have some transmission line, some load, if we make this a quarter wavelength, we can often find a way to match these things together. So what this is saying is that we have a 100 megahertz FM broadcast station, right? So this means this is the frequency, and it uses a 300 ohm transmission line. Between the transmitter and an antenna mounted half wave dipole. We want to design a quarter wave transformer to match the antenna to the line. Okay, so we have this, and we have some input impedance. And we want to find a way to match these, where this line length is a quarter wavelength. So this load is 73 ohms. And this input impedance, what this is saying is that it's 300 ohms. And if the length of this transmission wave line is a quarter wavelength, we can find a characteristic impedance like this that gives us a way to match the input impedance to the load impedance. Okay, so this is what the first part of this question is asking, is to determine the electrical length and characteristic impedance of the quarter wave section. And then in the second part of the problem, this is an actual design problem. So we have a quarter wave section, and we're saying that this is a 2 wire line transmission line. So we know that the length is quarter wavelength. And you can use this, you can determine based on the previous information what this is. Okay. And then you can use a table in the book to do this design. Okay. So we already saw that this is a lossless 2-wire. And we have this information about the 2 wires. And the 2-wire means, right, that it is, this transmission line really is built like this. There's 2 different wires that are separated from each other, right? The other types of transmission lines that we have seen are the lossless coaxial and the lossless parallel plate. And these are just 2 other structures that can guide waves on them. So same with this lossless 2-wire. So once you've determined, right, the characteristic impedance of the line, right, you can design this. You can solve this equation. So and then once you've solved for this quantity D, big D over little d, you can plug in the big D to find the small d. Okay, does that make sense? Let's try to.
Yeah, that does.
Okay. Then just going to try to walk through these a little bit quickly here. This one is very similar to the first ones we did, or the ones that we've kind of seen over and over in terms of we've built up our information that we can handle, right? We've built it up about what we know about transmission lines. So first we started pretty simple, just looking at reflection coefficient and voltages. Then we built up our knowledge of reflection coefficient. Then we said, well, let's include some line length in here as well. And let's handle the line length. And that's when we looked at how to find the input impedance. Then we said, well, we can also build this into full circuits, right, where we can handle the generator part as well. And we'll deal with that using the phasors. And from there, right, we can get all the way, we can build up our case all the way so that we are finally even doing things just like we did in the last homework, right, where we can find things like the voltage at the input, current at the input, and the voltage at the load, right? So this problem kind of brings together a lot of the things that we've covered already, similar to one of the last problems we did in the homework 10. Oops. All right, and then these last problems are about transients. So if you have watched the videos, what you should get from them is, right, sometimes, right, we have a transmission line like this, And we turn it on. But the transmission line, right, this voltage might be like a step function, right? So first, for a long time, right, we had no voltage, and then it steps up to 10 volts. And so what happens, right, when we do something like this, is we turn it on, and at the very beginning, right, and this on a time scale, right, of like nanoseconds or picoseconds, right, you turn this on, and at the beginning, right, it takes time for the wave to travel down this, right? This has a real physical line length, and it takes time for the wave to propagate down there. So the wave has to go down, right? And then what happens when you hit a mismatched load? What happens to some of the wave?
Reflect.
Yeah, and then some of it is going to reflect back. And then when it gets here, right, what's going to happen to that again? It's going to reflect back this way, right? Once it hits this impedance. And so this will happen a few times until you reach the steady state, right? So you're going to have some waves that are bouncing, from one side back to the other on this transmission line until your line reaches a steady state. Okay, and we look at this using this method called the bounce diagram. Okay, so we can analyze this transient effect. So the transient just means like it's a short amount of time, or it's not permanent, right? We haven't reached a steady state yet, so it's transient, and we can examine the transient nature of those waves using the bounce diagram. Okay, so what we can write this as is we can set it up two ways. Okay, where we have a voltage here and then a time axis here. Okay, down at the bottom. And on this side, we have z equals 0. And on this side, we have z equals L, where L is the length of the transmission line. So what we know is that the wave is going to first come down here. And we will call this V1 plus because it's propagating to the right down towards that load. Okay. And then once it arrives here, and this is where at the end of the load. So once we get to this side right here, right, it's going to bounce back. And we'll call this V1 minus. And then it's going to bounce again in the plus direction. And so on and so forth until we reach an equilibrium. And we can translate the voltage here based on these bounces to a diagram, a plot on this side that shows what the voltage is for any given point of time. So in this problem, we're asked to find the voltage at the center of the line, right? So this is at the center of the line here. So we want to find the voltage on the line at these points. Okay. Now, what do we need in order to do this? Well, we're going to need to know V1 plus. So what did we start with? And we can find this by using a voltage divider. And then we also need to know what is the reflection that happens at the load. So when we're at this side, right, we said there's going to be some reflection that comes back. So we need to know how much is reflected back. And we can use that information to figure out, right, we have, once we hit this side, there's a voltage that bounces back. And we can use that to determine that voltage that bounces back. And lastly, we need to know what the reflection at the generator is. So on this side, right, when the wave hits here and it reflects back, right, there's some generator reflection coefficient. All right, and once we know these, we can use these, we can continue to use these to find the reflection each time, right? Because to find V2 plus, right, that's the generator reflection multiplied by that incoming wave. And the V2 minus, right, we're back to this load reflection multiplied by that incoming voltage. Okay. Now the one last piece of information that we need to know is, right, this axis is time, right? So we have a time axis that's going down the page. Right, so this going down is time. So what we need to know now, the last thing is, what amount of time does it take to travel down this? Okay, so we have some line length, we have a length, and we have a velocity. So how much time will it take? So if the wave is traveling at a known speed, how much time does it take to travel from one side of this line to the other? So we have a length of 1 meter and a velocity here. So let's see if you can figure out how much time that's going to take. You know, when you have an answer. All right, anyone get an answer? It's just length divided by velocity, right? So that will give us meters divided by meters per second. So the unit will be in seconds.
Like nanosecond.
Yeah. Okay, so each one of these trips takes 5 nanoseconds. So this is the last thing we can mark here is we have 5 nanoseconds to get to from one side, from the left side to the right side, it takes 5 nanoseconds. Then from the right side to the left side, it takes 5 more nanoseconds. 15. And then 20 nanoseconds. Okay, now, can you determine what each one of these is going to be? Once you know all 4 of these, we can start this process and we can do this perpetually, right? So to start off, right, we had a voltage, the generator voltage of 60, right? And so we have 60 multiplied by the characteristic impedance of 50, and the generator voltage is 100. So we have 50 over 150. So we must have 20 volts here. All right, so this voltage is 20 volts. So the voltage V1, so as it bounces across, we've started this up, we've turned it on, we have this step voltage that turns on, and instantaneously, right, we have a voltage of 20 volts that starts bouncing this way. So when we get here, as it bounces across the center of the line, so it's traveling to the right towards the load, crosses the center of the line. And before this, right, we're way down at the load, and we're at the center here. And at this time, right, we don't have any voltage here, right? We're at the center of the line and no voltage has passed across, right? Then after we reach this, so at 2.5 nanoseconds, voltage 1 plus crosses the center of the line. And we know that voltage 1 plus is 20 volts. So it starts up all the way to 20. Okay. So now we're at 20 volts. And it's going to keep staying at 20 volts, right? Because the time, nothing has bounced back yet. So the wave is still propagating down to the load and hasn't reflected. It reflects here and comes back. But this whole time, right, the new wave we have not had enough time, right? We're on a time axis. We have not had enough time for the new wave to hit the center point. So we're going to stay at 20 volts all the way until we get to here. And at this point, right, we can see that the wave has returned and we've got down here. And we need to figure out what V1 minus is. Okay. So it's going to, once it hits, it's going to have some different value that's going to be V1 plus V1 minus at this point. And this process will continue on down the line. And you could do this for any point on the transmission line. So you could set your line, your dotted line here, you could set it to like a quarter of the length. You could set it to the generator. You could set it to the load. And what you're doing for all of these bounce diagrams is you're moving along the forward or reverse propagating wave, and you're waiting to see when it crosses your dotted line. And then you'll transfer that information to this side, where this side is a voltage as a function of time plot. All right, so I know this might seem like a little confusing. We're about out of time, but I'm glad we were able to get here. Does anyone have any questions about how to make these bounce diagrams? Okay, the main point to make is just that when we turn on a circuit, so just like we had to deal with when we have a high frequency and a long line length, we have to account for that in circuits. the same thing can happen when you have a long line. You have actual transient effects that occur inside of your circuit, and it doesn't reach steady state immediately. And so this is just a method that we have of considering how to analyze circuits that have not reached steady state yet. And so this is going to bounce around until we reach, we're going to bounce around at different voltages until we reach a steady state voltage where these bounces have almost no effect on the voltage as a function of time. The last problem on the homework is basically going from this voltage as a function of time back to calculating this information on the left side. So you can either go from knowing information about your circuit to finding the voltage, or you could go from knowing voltage as a function of time and going back and calculating these aspects of your circuit design. Okay. All right, well, I am happy to answer any questions. Class is over if you need to go, but I feel like I was going a little fast today. I just wanted to show you more how to start every one of these problems rather than working through each one.
Dr. Kreisler, I just had a question about the advising me.
Oh yeah, I need to do that for you. Yes. I'll do that right now.
Thank you.
Any other questions?
My question was not pertaining to this class, but to your RF class.
Yeah.
Are you using a book for that, or are you just going like freehand?
Yeah, I will use a book, mainly because there's this one book that's really famous. It's called Microwave Engineering by David Posar, and it's kind of this weird book that's, or it's like the weird case of a book that, a lot of your undergraduate books you probably won't ever use again. But this book is kind of weird because if you do happen to go into something like microwave or RF engineering, this is a book that like everyone uses. Like it's just kind of like a stand. If you work in that field, you probably have a copy of this book like sitting on your desk somewhere. And let me see. Yeah, this one looks like this. The international paperback. This book used to be super cheap. It's a little bit more now. If you buy like the brand new hardcover, it's like $100, but this book is very, very famous. And it is like essentially both a design handbook and a textbook. There's not a lot of books like that work just as well as a textbook, as well as it does with like as a professional reference handbook.
I have a question, like which edition we are going to use for this?
Yeah. I use the 4th edition mostly
I see.
because it's been out for a long time.
Yeah, I do have that one. That's why I'm asking.
Yeah.
The 4th edition, right?
Yeah, 4th edition.
Thank you.
I think too, Calvin, are you interested in having this book as a PDF?
I mean, yeah, I'd definitely read through it. I'm interested a little more in the RF side, rather RF and software rather than the hardware portions. But
Yeah, this book is I guess email me. It's pretty easy to find, if so. And if you can't find it, I can help you find it.
all right, sweet. Thank you so much.
Gabriel, questions?
No, those.
All right. All right. Thanks for joining, Zaya. Do you have any questions about next week, how to do the class?
No, like not now.
Okay.
If some question arise, I will like email you.
Okay. I do, if you might be able to rent like a iPad or something from the library so that you can, if you want to try to like write some equations or something. Otherwise, I recommend like having your hand solution or something available so you can just like share the screen. But it's
Oh,
up to
I see.
you. Yeah.
I see. I think I can use my hand solution, so it will be like easy to share with them.
Yeah. And once they finish next week, like if they don't have any questions, it's okay to end the class. They might not. Yeah.
Mhm.
I just want them to have a chance to like review and ask you any questions. So for you, I would say make sure I think you should have access to homework 11 solution and the practice problem solution.
Yeah. Uh-huh.
And just make sure that you know how to do all those problems.
Yeah. Okay.
So does most of this stuff seem pretty familiar?
Yeah, it's like everything is on like transmission lines problem, so it's quite easy for me. I
Yeah.
think so. I think I can like deliver them.
Okay.
like, all those things.
Yeah. Okay.
Okay, Dr. Krishna, see you. I have a class on 9:30.
Okay. All right. Have a nice day.
Yeah, you too.
Bye.
Bye.